All right, well, that's 2:16 by my watch, so that's as good a time to start as any. Hello, and thank you all so much for joining us for our second of two press conferences today. It is Monday, June 10th. We're here in Madison, Wisconsin at the 244th meeting of the American Astronomical Society. My name is Carrie Hensley. I'm the Deputy Press Officer for the AAS, and I'm joined today by Susanna Kohler, our Press Officer, and Ben Cassess, our AAS Media Fellow. Before we get started, I just want to remind everyone to please silence your cell phones or anything else that might make noise and interrupt our presentations. Press releases from this morning's presentations are available on the AAS Press Twitter feed, as well as on the website, along with the briefing video. And the slides from those presentations will be available soon. So, briefly, how this is going to go in case this is your first AAS press conference. I'm going to introduce our speakers and what they'll be talking about. We'll hear from our panelists in the order you see them sitting, and then we'll go to Q&A. So we won't break for questions in between the presentations. For our off-site journalists watching on Zoom, please a reminder to queue your questions using the Q&A feature in Zoom, and we'll get to those during our Q&A session. So today our press conference is titled Stars and Their Antics, Hearing What Stars Are Up to Near and Far. Our first speaker will be Adam Burgasser from the University of California, San Diego, speaking on a hypervelocity subdwarf passing through the solar neighborhood. So a nearby star indeed. Next, we'll have Janus Kozdon from Clemson University speaking on evidence of a multi-component eccentric disk induced by a planet around Ci Tau. Then we'll have Ravi Sankrit from the Space Telescope Science Institute talking about the long-term post-explosion evolution of a symbiotic nova. Then we'll have Cameren Swiggum of the University of Vienna speaking on uncovering 3 past massive star-forming complexes that shaped local interstellar structures. And finally, today we'll hear from Christa DeCoursey from the University of Arizona and Justin Pierel from Space Telescope Science Institute, speaking on some JWST results someday, many years after this telescope launches. I will be able to say that acronym without tripping over it. So JWST as a supernova discovery machine, catching roughly 40 new explosions in the JADES deep field each year. So with that, Adam, take us away.
Okay, thank you very much. Carrie, and thank you everyone for coming here today. I'm very happy to start off today's press conference with an interesting discovery we've made in the nearby universe, and that is a hypervelocity L subdwarf passing through the solar neighborhood. This is the result of a large team of researchers. You can see their names listed on the bottom. I've highlighted some of the students who are involved in this, and also some of the citizen scientists who've been involved in finding these sources as well. This discovery comes from the Backyard World's Planet 9 project. This is a citizen science project to discover faint red, fast-moving sources in the solar neighborhood. Main point of this project is to kind of find some of our nearest neighbors that we've overlooked from past surveys. But as a result, we're finding all kinds of unusual objects at the same time. And so you see some of the citizen scientists that have been helpful in identifying and discovering and going through thousands and millions of images to find the sources we're looking at today. All of this data is based on the WISE and NEO-WISE missions that have taken up to about 14 years of data in the mid-infrared. So they're perfect for finding these moving faint red sources. The source of interest today has this beautiful named, I'll call it J1249 plus 36 for the remainder of this session. It is a source that is incredibly faint in red. These are 2 images taken about 10 years apart, one from the Sloan Digital Sky Survey, one from the Pan-STARRS survey. And if you're an optimist, you might squeeze your eyes and see that there's some kind of smudge that appears to be moving across the field. Fortunately, with WISE, we're able to again get multiple years of images, and we can actually see this very clear, obvious infrared source moving quite apparently across the sky at a rate about an arc second per year. That's about 10 times slower than Barnard's star, but still a very fast star in our local neighborhood. To understand the nature of the source, we went to the Keck Observatory and used the NIRES spectrograph to get a near-infrared spectrum. That spectrum is shown on the figure to the left as a black line, repeated 3 times because we compared it to 3 different types of low-temperature objects. The top one is what we'd call a normal L dwarf, object that's somewhere between a star and a brown dwarf. That has a temperature about 2000 degrees Kelvin. Not a very good match. And in fact, what we were finding is that this star was a much better match to what we call subdwarfs or metal-poor L dwarfs. And these are objects that have less heavy elements than the sun. And so you can see that the bottom two spectra are slightly better matches, and that allows us to classify the source as a metal-poor L subdwarf. Now, these data have also allowed us to actually do more quantitative analysis. And so we used a new set of atmosphere models that were developed by my students who are here in the room called the SAND model atmospheres. And these were able, for the first time, to give us a very precise measurement of not just the temperature, but also the abundances in the source. And so we found that this indeed was a metal-poor object at a temperature about 2000 degrees Kelvin. And just for reference, that's about the temperature that melts steel. But of course, the sun is about 3 times hotter than that. So this is still a cool star. In addition, these data were able to provide the resolution, the spectral resolution, to measure the radial velocity. And we do this by a forward modeling approach where we take the spectrum and we compare it to a model that includes both a model of the star, which is in blue, and a model of our atmosphere, which is in green. And the combination of those allows us to very precisely measure both the wavelength scale and also the motion of the star. And so we're able to measure the radial velocity, which turned out to be quite large, about 100 kilometers per second. But that's no comparison to the total speed of the star. When we combine the radial velocity and the tangential velocity, we get an incredibly fast speed, which we'll see in a moment. So just to recap, these spectra have allowed us to measure all kinds of physical properties for the star, including estimating its mass, which we estimate to be about 8% the mass of the sun, and its distance, which is about 125 parsecs or 400 light years, so relatively close. But again, the exciting thing was this star is moving very fast, about 456 kilometers per second in the rest frame of the Milky Way. It's actually moving faster relative to us here at the sun. That's, for translation, is about 1 million miles an hour, or about 1.1% the speed of light. And at that speed, it's at a rate in which it's possible that this star can actually escape the Milky Way. So to illustrate this, this is an animation of the star's orbit. It's going to change very rapidly at the beginning because it's moving so fast. And as you see, as it launches itself out at that rate, it's going to get itself out to roughly 180 to 200 kiloparsecs, so 180 to 200,000 parsecs away from the galaxy, at which point it may turn over. But of course, with our uncertainties, something like 20% of our trajectories just leave the Milky Way entirely. So this looks like a source that has a possibility of actually leaving our Milky Way. Here's another picture of that orbit compared to the locations of some of the satellite galaxies that orbit the Milky Way, and it's approaching the kind of scale distances for those systems. We also projected its orbit backwards in time to see if we can figure out where the star came from. And on that side, on the right image, is the locations and orbit trajectories of the globular clusters that we've measured velocities for. And while it comes close to some of these, it actually doesn't intersect with any of them. So we're still not quite sure where the star came from. We have a few ideas on how 1249 got its kick. One idea is that it may have been part of a binary system with a white dwarf that exploded. In fact, the star that we're looking at may be responsible for that explosion. Don't tell anyone. Because by contributing mass to that white dwarf, it may have caused it to go beyond its Chandrasekhar limit and blow up, and as a result, escape the system entirely. There's also a possibility that this is a star that originally was in a globular cluster. Its metallicity is consistent with that. And there are models that show that you can have these dynamical interactions, particularly with black hole mass binaries, which can kick these stars out to very high speeds as well. And of course, our third possibility is that it's just an incoming neighbor from either a satellite system. Again, we are not quite sure of any of these because we haven't found the progenitor systems. So just a quick couple of simulations. This is a case where if this was a very close companion to white dwarf that then subsequently exploded, kaboom, the complete destruction of the white dwarf in that case would have released the star to just continue its motion, its orbital motion in a straight line at a speed of about 500 to 600 kilometers per second. And then if this is a star that happened to pass by a globular cluster, this is not as exciting of a demonstration, but as it gets closer, it gets pulled in, but then gets pulled back out at a higher speed because of the presence of the secondary system. And again, our collaborator, Kyle Kremer, was able to show that this can happen at a very low rate, but it's possible in some globular clusters in our system. So I'll leave with just some of the key results, summarizing what we know about this star, that it's nearby, metal poor, and very low mass. It has an incredibly high speed, and it's sufficient that it may actually be escaping the Milky Way. We've explored 3 different possibilities for how this star got its very high speed, none of which at this point we all know they are feasible, but none of which we've been able to prove quite yet. And the analysis of the elemental abundances with future spectroscopy may provide that kind of elemental fingerprint that will allow us to figure out exactly where this star came from. So I invite you to visit my poster on Thursday on this, and I also invite you to see a talk by Roman Gerasimov, who talks about some of the applications of the models, and Efrain Alvarado here in the audience, who will be talking about the models themselves. Thank you very much.
Hello, everyone. I'm Janus Kozdon, and I'll be sharing the results of a paper I released last year pertaining to the protoplanetary disk around the star Ci Tau. So, very young stars are still in the active process of collecting and accreting material. This material will eventually settle onto a common rotation frame, and this is what a protoplanetary disk is. And in a protoplanetary disk, that is where planets will also form. When this planet forms, it will also start inducing substructures in the disk. Like in this left image, we see a disk that has a concentric feature of rings and gaps, presumably due to planets, and stuff like that is actually very common. But the planets responsible for those features themselves have very rarely been detected. The few examples that we have are the stars ABR and PDS-70. However, the location of those proposed planets with respect to their disks, they are located in a more depleted location of the disks already. And so to use these stars as an example for studying active planet-disk interactions makes these stars subideal. But we do have a star called Ci Tau. Now, currently, Ci Tau has 4 planets attributed to it. This star is only 2 million years old, which makes it one of the youngest stars to host such an ensemble of planets. The one of particular here is the closest in planet, which has been verified to exist by studying the star's radial velocity measurements. And from other observations, this planet is still located in the part of the disk that has not been depleted yet. And so we can use this star as a case study for studying planet-disk interactions since we already know the planet exists. To study the protoplanetary disk around Ci Tau, I construct a model that replicates the kinematic behavior of the disk. On the right side, on the top, that is supposed to be a disk, and the different colors are the contours of the projected velocities of the orbiting material. If you make a plot of the emissions of the disk in accordance to those contours, you get a line profile that looks like the thing on the bottom right. And so by studying a disk's line profile, you can also determine its geometry. Ci Tau's line profile looks like this. And on the bottom right, when we tried to fit it with a circular disk, we weren't very happy with that. We also weren't very happy with fitting it with a normal eccentric disk. And so what we ended up doing is that we took Ci Tau's disk and we broke it up into 2 components, each of which had the freedom to be eccentric, but oriented in opposite directions. There is a schematic on the top there to highlight this, but I also just made it bigger for you. And to repeat, in this image, we see the purple inner disk. It is eccentric, oriented to the top left of the image. The outer green disk is also eccentric, oriented to the bottom right. And this phenomenon here of this disk potentially being bisected by the presence of a planet, this may actually be the first time that has been observed. The break in between them, which occurs at about 0.14 AU, could be a potential gap. And some follow-up studies after my paper came out also reported the location of potential gaps and planets in this disk, and they appear to be consistent with where I placed it from this study. And that is exciting. And so the conclusions are that from studying Ci Tau's protoplanetary disk, I have determined that it is what I call a multi-component disk with a potential gap located at 0.14 AU. And this could be the first empirical evidence of disk eccentricities that have been induced by an embedded planet. Thank you.
Good afternoon. I'm Ravi Sankrit from the Space Telescope Science Institute, and I want to tell you about the long-term post-explosion evolution of a symbiotic nova. This is work done, a lot of it with my close collaborator, Steve Goldman, also at STSCI, and several others. And I'd like to call out the first two, Carlo Goldoni and Simon Bosoni, who are AAVSO observers, and Nathan and Sean were interns working with Steve. So this is an asterism, Sagitta, the arrow. It's a beautiful constellation, one of the smallest ones. And if you can see that small purple crosshair, that's where HM Sagitti is. I'm going to show you a blow-up and show you that it's a very nondescript star, even amongst the faint stars. However, this is the star that I want to talk about today, HM Sagitti. What happened was in 1975, it brightened by 6 orders of magnitude in the visual. And this is a later paper which shows the light curve and how over a period of months it went becoming hundreds of times brighter. And very soon after this outburst in 1975, people took spectra of it. And this emission line spectrum showed that it was what we call a symbiotic nova, this and other studies. And what is a symbiotic nova? What it is a binary system with a white dwarf and a cool mirror red giant. The mirror variable is typically dusty. It has a period of oscillation, and they're orbiting around each other. And the components are fairly widely separated, and they're usually in an eccentric orbit. And then the accretion is not constant as in when things are orbiting very close to each other, but more episodic and uncertain. And the material builds up on the white dwarf surface, and then quite unpredictably, it outbursts, and there's a thermonuclear outburst, and it becomes brighter and hotter. And then when that happens, the system remains in this bright, hot state for years or decades. Some years ago, there was an opportunity to use the Hubble Space Telescopes and SOFIA in a director's discretionary program to to propose for observing various objects. And Steve and I decided that HM Sagitti would be something that's worth looking at. And so we proposed for it, were successful in getting the proposal through. And then we initiated with the AAVSO, and a big shout out to the AAVSO, to follow HM Sagitti. Now, this light curve shows you that people had been looking at HM Sagitti over the years, and it was going down slowly in brightness, as you can see in RV and B. And the bunch of points towards the right end is after we started a campaign, and we requested the AAVSO and said, please observe this as often as you can, and they did. And then you could see the sort of rather sudden decline, which is really interesting when you don't know the answer to why that's happening, but it may be like some kind of dust cloud that's obscuring the system. So this is sort of the background of what HM Sagitti is doing. Now I'll go through to the various data that we took. Separated, and this is where the long term comes in. This was 20, 25, 30 years after previous observations of similar kinds. And this is the silicate features from the mirror variable, which is the cool companion. It was looked at with IRAS in '83, ISO in the '90s, and then with SOFIA forecast in 2021. And the silicate features are from the circumstellar dust around the mirror. And what they show is that pretty soon after the explosion, the mirror variable itself seems to have settled down to what it was like before. And it's basically pulsating to about 520-day period. The next was the inner nebula, which was observed with HST WIFPIC-2 back in 1999, and we got observations with WIFC-3. And this is really about 1,000 AU, 2,000 AU, right around the binary. And what I'd like to point out is this incredibly dramatic change in the morphology that has happened in those 20 plus years. And the oxygen-3, which is photoionized, is just changing due to all the outflows going on in this system. And the next is the ultraviolet, and this is something I'm going to be presenting later at this conference, so I'll spend a minute, an extra slide on this. We looked at it with COS on HST about 30 years after the International Ultraviolet Explorer had looked at it several times in the 90s, in the 70s, 80s, and 90s. And the COS aperture is projects about 2,500 AU on the nebula. But all the emission in the ultraviolet is coming from really close into the binary where you have photoionization and you have colliding winds that are creating a shock. And this is the spectrum, the spectra that we see in the far ultraviolet and the near ultraviolet. And these are just spectacular. And I'm going to focus here on a few lines. And you can see on the right in blue, it's what you see with what we saw with IUE, or people saw with IUE back in 1989, and the orange is what we see with COS. And you can see, if you look at pairs of lines like neon 5 and neon 4, that the higher ionization line has increased relative to the lower ionization line quite dramatically. And I want to point out the magnesium 6, which was not present in 1989, has become as strong as the magnesium 5 in our COS data. And what this shows is that the central white dwarf that's heating up, that it went into outburst, has increased in temperature, effective temperature, from a black body, call it a black body temperature, of less than 200,000 Kelvin to greater than 250,000 Kelvin. The other thing to notice is nitrogen-3, which is lower ionization than all of these, has remained about the same, which indicates probably it's coming from a slightly different place, and we think it's from the shock between the colliding winds that persists to this day. So I'm going to end with the current sort of what our summary is, which is HM Sigeti has evolved in very interesting ways in the last 20 to 30 years. With SOFIA and HST, we looked at the infrared, optical, and UV, and they probe different components of the system. The cool dust-producing mirror variable appears to have relaxed. The extended nebula has expanded. Its morphology has changed as it's being fed by the outflow. And the ionizing source has become hotter, and the shocked region persists. So our next step here is to build up a more complete picture, taking all these different multi-wavelength data and seeing what it means for HM Sigeti. And then we want to outline the ways in which we can identify symbiotic novas as ongoing time domain studies and try to figure out how we can learn about them using HM Sigeti as our template. And what I'd like to leave you with is this triptych, which kind of shows the wonder of the night sky, the excitement of a transient phenomenon, and the beauty of spectra that allow us to actually probe and learn what it's all about. Thank you.
Hi, my name's Cameren Swiggum. I'm a PhD student at the University of Vienna, and I'm really excited to be here today in my home city of Madison, actually, to present this work that was just recently published this morning in Nature. And first, I want to highlight this results wouldn't have been possible without this great collaboration that I have listed here, including my advisor, Joao Alves in Vienna, and Robert Benjamin, who's a professor at the University of Wisconsin-Whitewater. So when we look up at the night sky, one of the key features that we can see that the human eye can see unaided are star clusters, open clusters of stars. And what we've known for a while is that these star clusters are born together with their siblings in their natal star forming regions. And then after some time, they leave these gas regions. And so for the star clusters surrounding the sun, one of the outstanding mysteries has been that we don't know where many of these clusters have actually come from in the first place. We don't know where their past natal star forming regions actually were. So this is kind of changed with the advent of the Gaia Space Telescope. So what Gaia allows us to do is it allows us to measure the precise positions of star clusters and actually begin to map where they are on the galaxy. So what I'm showing here in the background here is an artist rendition of our Milky Way. And so we're going to zoom in on where the sun is located on this map. And so now you're looking at this 5,000 light years by 5,000 light years box. And so here's a map of the star clusters that surround the sun. And one thing that I want to point out here is that every one of these gray points that you see here on this map, this is one star cluster. So there's 155 star clusters that I'm showing here, but each one of these gray points is a collection of stars. And so the other thing that Gaia provides for us is the precise 3D motions of star clusters. And so what that means is we can take the velocity vectors that we see for each of these star clusters, and we can just flip it backwards, and we can trace where these clusters, we can trace these clusters backwards in time and find where they actually came from. So that's exactly what I'm going to show here. We're starting at the present day, and so now you see this arrow here that's kind of tracing this circle. This is kind of the galactic racetrack that we're gonna travel backwards in time along. So I'm gonna play this forward. So now you can see as I play this forward, we're going millions of years into the past, and we're seeing the locations of where these clusters were in the past. So I'll go back to the present day and play this maybe a couple more times. So here's today, 10 million years ago, 20, 30, and maybe one more time faster. And so one thing you begin to notice immediately is that when we go back to 30 million years ago, we find that all of these clusters are converging to one of 3 points. And so what this means is that these are young star clusters that are forming in families. So we are actually finding where these massive star forming regions were 30 million years ago and beyond. So the special part about this is that we're actually tracing most of nearby young star clusters surrounding the sun to one of these 3 families. So we're providing the origin stories for most nearby young star clusters surrounding the sun. And so we know, or we can tell that these three families of clusters formed in these massive star forming regions. And since these regions were massive, what this means is that they produce massive stars, and massive stars tend to explode as supernovae. So when we take all 3 of these families together and we calculate how many supernovae we infer how many supernovae they've produced, we find that they've produced likely over 200 supernovae, which is a big number. And what this means is that since supernovae inject a lot of energy and momentum into the surrounding interstellar dust and gas, what that means is when we compare the location of these star clusters to the present day distribution of dust, as we can see here from this 3D dust map that's projected again on this galactic map here, what we can see, at least in this example with the CR135 family, we can see that these star clusters are located within these dust cavities. And so this example that I'm showing here for the CR135 family is actually located and forms this galactic supershell, which was first discovered in the 1990s. And this shell is 3,000 light years wide. So we're sort of providing this time-resolved view of the formation of a massive star-forming complex that produced supernovae and drove the expansion of this galactic shell that's within the environment of the sun. So I'll leave you with the summary. The main point is that we're tracing most of the nearby young star clusters back to one of these 3 regions, into one of these 3 families. We know these families, or we can infer that these families, the gas regions were massive. And because of that, they produce supernovae. And we can directly relate the explosions of these supernovae in these families to the present day distribution of dust and gas that surrounds the sun. Thank you.
Sorry for anyone online listening. We're having some technical difficulties here. They're trying to get the audio back from the main room.
Gonna all of this out and move it to the slide. Yeah, I think like Howard too, like some.
It's not the
It's
same.
not the same. Oh, well, I might die, but it's.
But we're not on Zoom anymore. So. Or
We are, we are.
Are we still on
YouTube?
YouTube?
Yeah, because Ben was made co-host.
Okay.
So we should be fine. Full screen. Yeah, under full screen. Oh. Okay, well, it might, oops. Can I not move this? No way to grab it.
More hide controls.
Brilliant. Okay, well, it is what it is.
Thanks.
Yep.
Do you need to check anything else, or are we good to go?
Are you good? You still hear me on Zoom audio? All right. Good afternoon. My name is Christa DeCoursey, and this is Justin Pierel. And we are presenting the JADES Transient Survey on behalf of the JADES collaboration and the TSSST team. So just to give some background context, JADES stands for JWST Advanced Deep Extragalactic Survey. And we took two sets of images of a very small patch of the sky. It's actually so small that if you took a grain of rice and held it at arm's length, that would be the size of the patch. Two sets of images over the course of 1 year. And we spent over 100 hours of JWST time on each image. So these are very, very deep images. And by taking them separated by 1 year, that gives us a chance to find things that either appear in the second set of images or disappear from the first set of images. These are called transients. Supernovae are one example of transients. And so we can go back and forth between the two sets of images, with this being 2022 and this being 2023, and you see something appears. These are supernovae. And so this is how we find them, just by comparing the two different sets of images. And so the first set of images was taken in 2022, and we didn't yet have those 2023 images. And so what we could do then was compare against HST images that were taken in the early 2010s. This was over a region covering the Hubble Ultra Deep Field. So we did have fairly deep Hubble images. But again, with this comparison, we were limited by HST's abilities. And so we only found 5 in this area, and those are indicated by the red dots in this image, where size is the brightness of the supernova. Once we had the 2023 images and did the comparison, this is what we found. And so you can see that we're finding dozens more supernovae with JWST as opposed to HST. There was 83 that we found compared to 5. But the thing that makes this sample so special is not just that we're finding so many more supernovae, but we're finding significantly more distant supernovae. And so the top row of this diagram shows the 2022 images, and the bottom row shows 2023. And you'll see on the top left, that's a supernova that we found at redshift 3.8. And so it exploded when the universe was just 1.7 billion years old. And it's there in the bottom panel, the bottom left, indicated by the cyan arrow. There's a small dot there that you'll notice is not there in 2022. Same thing in the center panel. It's not there in 2022, but if you look at the 2023 image, a little bright dot appears. And that supernova exploded when the universe was just 2.3 billion years old. On the right side, we show a very large spiral galaxy, where you'll notice there is a bright dot there in 2022 that has disappeared in 2023. And this exploded when the universe was 8 billion years old. And so now this diagram at the bottom shows the Big Bang and then the history of the universe. And so time proceeds from left to right, where the left is when the universe is in its infancy. And then towards the middle, it's a log scale. So it's not linear. The universe is equivalent of a child or a teenager at the center of the diagram. You can see that the galaxies are starting to form. And then you keep moving towards the right, and you get to the young adult phase of the universe when it was around 4 billion years old. And this is the regime that HST can target. And over the past 20 years, HST has found roughly 20 supernovae in this regime. And then even further to the right, we get to the adult and elderly phases of the universe. And we've found tens of thousands of supernovae in this regime with ground-based telescopes. But this JWST sample is so special because we're probing when the universe was a child and a teenager. And so we have found over 40 supernovae within just 1 year in this region.
Just gonna jump in and emphasize that these supernovae, it's not just about how many we're finding in this new redshift range, but really the universe was fundamentally different at this early phase than the times that Hubble and particularly ground-based surveys were probing in the past. This is a time where galaxies had very low or no metals, because those heavier elements were formed by the supernovae that we are now finding for the first time. And so this is really a new regime that JWST has opened, and it's basically the only resource that is capable of doing this. looking to the future, we're expecting to push this to really the first stars. So population 3, the very first stars, is one of the primary objectives of James Webb. And while we can see galaxies at these early phases, learning things about the individual stars in those galaxies is really beyond the capabilities of James Webb, but it can see the explosions of those stars. And so that's something that we are expecting to find with targeted surveys in the next few years. Beyond the first stars, type 1a supernova cosmology, so measurements of dark energy using these special type 1a supernovae, is something that James Webb is capable of expanding to redshifts beyond anything that something like Hubble or even something like Roman will be able to achieve. Even from just JADES, this 1 year, we were able to extend it to redshift 3, and we expect to go beyond that with some more special surveys that we have planned for the next couple of years. So we found some really surprising results in this, which we have summarized in these first few papers. I'm sure there'll be more to come. So you can follow these links, and also, of course, we'll be happy to answer any specific questions about these in the Q&A. Thanks.
For both. There we go. Audio.
Confirm, Ben, that we still have audio on Zoom. Test. Yes, wonderful. Okay. Are we still in like the screen share mode? Oh, we don't have the background. No, I just would like to be not sharing the screen. I am in the room. Yeah. Yes. Yeah. Well, if you want to start the Q&A section. Yeah, sure, absolutely. Excellent. So now time for us to begin our Q&A. So a reminder for everyone in the room as well as everyone watching on Zoom to please state your name, affiliation, and who you'd like your question to be directed to. So do we have someone can grab the microphone in the room? Thanks, Ben. All right, so questions here in the room, if there are any.
Yambo Penn, University of Michigan. This question is addressed to Cameren. So Cameren, when you are doing the backward velocity tracking for the star clusters, do you consider like those factors to change with time? Like how do you model those factors?
Yeah, so that's a good question. So for the galactic potential that we assume, we just assume a simple axisymmetric galactic potential. So that means is we don't consider these time variations in the potential. So that could be that's definitely a source of uncertainty in terms of tracing these clusters backwards in time. But what helps us is what we're actually observing in the first place, which is convergence of clusters. So we're seeing these clusters start from these spread out points and converge to these 3 regions. So we know at least that in this sense, the potential model for this time range is okay, but there's probably some uncertainty. We're probably missing some stars that could have been deflected by any local changes to the potential.
Thank you.
I'm Julia Scheffler. I'm with UW-Madison. My question's for Adam Burgasser. I was wondering if you could talk more about what abundances would help you distinguish and why they would help you distinguish between those different methods for giving this a kick.
Yeah, thank you very much for your question. So there's the overall metallicity, but we are particularly interested in things like the alpha abundances because that will depend on what kind of globular cluster, if it's from a globular cluster, it came from, but also what kind of pollution it may have received if it was a white dwarf explosion. So what elements may have been deposited into the atmosphere as a result of that explosion. So broadly speaking, things like carbon, oxygen, magnesium would be elements we want to get more information about. But of course, even other detailed elements may help us if there are specific globular clusters we can start to narrow down.
We have one online clarification question also for Adam. This is from Andrew Fracknoy asking, what is the velocity in our sun's frame of reference?
The velocity so in our frame of reference, the velocity of the sun is very small because we are very close to the sun. In the galactic frame of reference that we're using, we're assuming that the local standard of rest, the sun has a speed of something like 20 kilometers per second, but in the galactic frame of rest, it's moving about 220 in a circle around the Milky Way, just like the image we saw earlier with the clusters. So that's what we're assuming to correct from that to what we take as the rest frame velocity of the star we're looking at.
Okay, I have several questions that I'm happy to have answered by my captive audience here. Sorry, guys. So first for Christa and Justin. So you've shown that there's a huge difference in the number of supernovae discovered by JWST in just 1 year compared to Hubble over the course of 2 decades. So I'm curious, is this difference just because of the wavelength range, the sensitivity, or is there even something about the rate of supernovae as JWST is looking closer to cosmic noon?
It's a combination of a few of those. The big difference is that JWST can probe to significantly fainter magnitudes. So a lot of the supernovae that we found with JWST were, 28, 29, 30th magnitude. So HST just wasn't capable of seeing those given the limited amount of hours it could observe. As for rates, that is future work. We're planning to probe rates beyond Redshift 2 in a future paper. There was one more point you had mentioned. Wavelength, yes.
Wavelength, yeah.
Well, the wavelength also allows us to find those further supernovae because of the redshift into the infrared regime that JWST can find.
Great, thank you.
Can I just add one? One thing I just want to add is that while we are, like Christa said, looking at rates of normal supernovae extending to these new high redshifts, one thing that we already found that is interesting is a couple of peculiar supernovae that we know of at lower redshift, but we think are more rare. And the fact that they were some of the first supernovae we found might mean that their rate at high redshift is higher than we thought. So that's something else that we're expecting to find with the next new samples.
Great. I can keep going if there are no further questions in the room. Do we have one here? Great.
Julia Scheffler, UW-Madison. I have a question for Cameren Swiggum. I was wondering how young your clusters are, because you say that they're young clusters, but I was asking for like an age range.
Yeah, sorry. I should have put this on there. They're all less than 70 million years old.
Oh, okay.
Yeah, so relatively young, but not the youngest. So the youngest ones are 5 million years old. These are clusters within Taurus and Kozdon. But the average age is probably around 30 to 40 million years old.
Thank you.
Yep.
Hi, I had a question for Ravi. This is Burgasser, AAS. What can you say anything about the timescale between outbursts in this system? How lucky were we to have caught the one in the 70s?
Yeah, thanks. Timescales are really unknown, and they could be for a comparable system with which is our Aquarii, which has an orbit that's closer in than HM Sagitti. They're thought to have been explosions maybe like 150 years ago, as well as 650 years ago for that system. For HM Sagitti, there's been no previous known explosion, and there's no shell of gas that's detected around it. So it was probably like, if there was any explosion, it would have been thousands of years ago, and whatever evidence for that has gone. So it was very lucky. And it was also lucky that it this is the most recent, one of the most recent such symbiotic novae, and it happened at a time when the ultraviolet spectroscopy could kick in within a year or 2 years of it happening. So it was extremely fortunate.
Okay, I've got another question. This one's for Janusz. This is a clarifying question that's almost certainly going to have a follow-up. So first, you have this key result that you have an inner disk that's anti-parallel from the outer disk. Just does that mean they are in the same plane but rotating in the opposite direction?
They are in the same plane with each other. They are orbiting in the same direction. It's their argument of periaps are anti-parallel to each other.
So that, I feel like, begs a lot of questions about how this situation arises. Does that tell you anything about the planet formation process in this system, or anything else about the orbit, like the evolution of this system?
We can use the geometry of the disk as a way to help constrain the properties of the planet itself that's causing it, stuff like the mass, the location, eccentricity. But it can also give us a way to go into the other parameters of the disk, like a disk aspect ratio, viscosity, and whatnot.
Great, thank you. I've got one more if we have time for that. Okay, so for Adam, you have presented this object that has the tantalizing possibility of someday escaping the Milky Way, which raises an even more eyebrow-raising possibility that objects from other galaxies could someday enter our own. Space is famously pretty big and pretty empty, so that's not overly likely. But what kind of things would you be looking for in terms of trajectory or chemical abundances to detect if another object is coming into the Milky Way?
Yeah, great question. And I would say, just like you were mentioning how lucky we were to catch this explosion, I think we're very fortunate to have caught this source, because it's actually passing right through the Milky Way plane, even though it's projecting outwards. And so that was one of the reasons that we thought it was unlikely that this is coming in from another system. But of course, we do have stars that have come in from mergers from other satellites. The Gaia-Enceladus merger is a good example of that. So we have these stars that have come in from other systems. And they do have distinct abundance patterns, although a large galaxy like what have merged with Gaia-Enceladus actually has a wide range of abundances.
Right.
So that's actually a less specific fingerprint than if we could figure out if it was a globular cluster member. So yeah, it's going to be a mixture of ideas, and until we find kind of the specific cluster or the specific abundance pattern that would tell us it was a white dwarf explosion or a globular cluster, that would remain a possibility that would be hard to discard.
Yeah. So you could have the same kind of ejection mechanism and then some 250 million years of crossing intergalactic space. Yeah.
Okay.
Sorry,
So I think it would be more likely in this case, particularly because it's a very eccentric orbit, that it's just come in with its galaxy, not necessarily thrown out of the galaxy, but it's part of the merger products. We looked at its trajectory, whether it came from Andromeda. It's just not in the right direction. So it's unlikely it's from those places, but it could be something that's actually kind of merged in now. Yeah.
Cool. Very cool. Thank you. Do we have further questions in the room or online? If not, then we can call this session to a close. Thank you so much to all of our speakers for your excellent presentations, as well as for the PAOs for helping to produce these press releases. We'll be back here tomorrow at 10:15 a.m. to hear about discoveries from the galactic center to the galactic disk. And yeah, let's give our speakers one last round of applause.